So we start now. So last class we were talking about strengthening mechanisms. We talked about strengthening mechanisms in pure metals to some extent. We will continue with that now and try to also look at the alloys. So just to recapitulate some of the things, we started saying what are the various strengthening mechanisms in pure metals. We talked about the dislocations acting as obstacles for the dislocations, and even before talking about strengthening mechanisms we talked about how a strength of a material can be increased by increasing the difficulty for the dislocation movement. We talked about this, we talked about slip and things like that. And so dislocations themselves can be obstacles for the other dislocations to move. So this is what we talked about as strain hardening, and the yield stress being proportional to the dislocation density to the power half. And then the next obstacle is the grain boundaries. Here also we talked about the Hall-Petch relation, and we also talked about how one can decrease the grain sizes. We will also look into it a little more detail. And the other possibility is vacancies. Vacancies themselves can be obstacles for the dislocation movement when you have a large number of vacancies. How do we generate large number of vacancies in a material? Quench it, yes. This is what is called quenching, quenched in vacancies we say. So we know that the vacancy concentration is always a function of temperature, and I hope you must have seen expressions like this. Cv is equal to some C naught or n, whatever you want to call it, exponential minus Q by RT, where Q is nothing but the activation energy for the creation of the vacancy. So we know from that that the vacancy concentration keeps on increasing with temperature, and if you go to a higher temperature you will have higher vacancy concentration. From there suddenly quench it to room temperature, you will have more vacancies. In fact, we many times use these vacancies as nucleating sites for the nuclei during the precipitation hardening. So many times whenever you quench it from high temperature, then the nucleation rate increases because you have large number of vacancies available which can act as nucleating sites for precipitates. So vacancies themselves can be obstacles for the dislocation movement. Because why? Because around every vacancy there is a strain field. Imagine you have atoms, and in the center of a number of atoms which are regularly arranged, you have a vacant site. The moment you have a vacant site at the center, then immediately the atoms around that vacant site are pulled inside. So you have some kind of a compressive stresses there. So you have a stress field around every vacancy. Like we say, there is a stress field around every dislocation. So similarly, there is a stress field around every vacancy, and this stress field is what acts as an obstacle for the dislocation to move. Okay, and so this is another possibility, and another possibility is stacking faults. Whenever you have stacking faults, we know those are the defects which are basically the distance between any two partials, dislocation partials, and this stacking fault width is the one which decides particularly how difficult or how easy for a material to deform. And you must have heard about cross slip, particularly when we talk about high temperature deformation. So we know that the two partials have to merge, then only you can have the dislocation movement possible, so that you get a unit dislocation, and that unit dislocation only can move. Partial dislocations cannot really move. So as a result, the smaller the distance between the two partials, that means the thinner the stacking fault width it is, the better for us as far as the cross slip is concerned. So that depends on something called stacking fault energy. You are all aware that the higher the stacking fault energy, the smaller is the width of the stacking fault. So materials which have high stacking fault energy, the width is very small, that means cross slip is very easy. So those materials can easily deform. The materials with very low stacking fault energy, for them the creep is more difficult because the stacking faults are much wider. So as a result, the cross slip is very difficult. So whenever we want to use a material for high temperature application, we always look for materials with low stacking fault energy. That is why we intentionally add also elements which can decrease the stacking fault energy. For example, nickel. has a very low stacking fault energy. So when you add to iron nickel alloys have very low stacking fault energy, and that's why we use iron nickel alloys for high temperature application. For example, Inconel is one such alloy which is nothing but an iron nickel alloy. So whenever you need high temperature strength, one way to improve the high temperature strength is to have low stacking fault energy. So add all those elements which can reduce the stacking fault energy. That is as far as the alloys are concerned. But at the moment we are talking of pure metals. So in the pure metals, among the pure metals, if you have more stacking faults, if you can generate stacking faults inside a material, you can increase the obstacles for the dislocation movement. So that's what one way of increasing the strength of the alloy. So let us again look back some of these. So we talked about the grain refinement and how by grain refinement we can increase the strength. If you have fine grain material, the large number of grain boundaries are there. Each of this boundary acts as a nucleating acts as obstacle for the dislocation movement, and hence you can increase the strength. And there are a number of ways to grain refine. And before that we also talked about why do you want to grain refine? To improve the strength, to improve the toughness, to improve the machinability and the good surface finish. And I told you about various techniques to grain refine, and the most popular technique is the heterogeneous nucleation. And when you have a large number of these kind of heterogeneous nucleating sites, such as intermetallic particles such as TiAl3 or TiB2 particles, which can act as nucleating sites for the aluminum during the solidification, when you add a master alloy like this, aluminum 5 titanium 1 boron master alloy, to a liquid metal and then start casting it, this liquid metal will contain these particles, and these particles act as nucleating sites when the solidification starts, and that is what gives you fine grain material. So that is the most popular technique. And we talked about what is called the ideal grain refiner, the fast acting and the long lasting, and we also talked about the grain refiner that has been developed at IIT Kharagpur, and a comparison of the macro structures of aluminum achieved by adding this grain refiner, and comparison with the imported grain refiner which is called London Scandinavian Metals Company. So this is the most popular grain refiner as far as aluminum industries are concerned. We talked about how we can get much finer grain size when compared to this. And if you look at the actual grain sizes which have been calculated, how do you measure the grain size of any material? Metallography method. What kind of a technique you use?
Project the microstructure on a screen.
On a screen?
Two straight lines and then
correct. What is this technique called? Linear intercept technique. Okay, linear intercept method is the one what we say. So you have a line of a known length to you, and then try to see how many grains intersect that particular length of a known length, line of a known length. And at a particular magnification, usually people use 100x as a magnification. So at 100x you try to see how many intercepts are there. That is why we say linear intercept. And then if you see a number of such regions to have better statistics, you can get an average grain size. One can also talk about standard deviation and things like that, and get an average grain size. And if you look at the grain size of the alloy which is developed at IIT Kharagpur, which is called alloy A, which is having much finer grain size than the two imported alloys, whether it is LSM or Anglo Blackwells. These are the two grain refiners. When you add those grain refiners to aluminum, these are what the grain sizes that you get as a function of holding time. So that is why we say this alloy is not only fast acting but also long lasting, because it gives you, for example, if you look at this, within 2 minutes of adding this grain refiner, you get much finer grain size. From this to this, you can see what a dramatic change in the macro structure. And similarly, even if you hold it for a very long period of 2 hours, you don't lose any of this grain refinement which you have achieved at a very short holding time. That is why we call it also a long lasting grain refiner. And if you look at that on a aluminum 7 silicon alloy instead of only aluminum, okay, this is where we are deviating from pure metals and going into the alloys. Aluminum 7 silicon alloy, many of you metallurgists know, it is basically a hypoeutectic alloy. Aluminum silicon is a eutectic system, and you know where we use these aluminum silicon alloys? They are all casting alloys. And where is the most yes, engine blocks in automobiles. So the most popular application of aluminum silicon alloys is the engine block application in automobiles. Most of the automobiles that you see, all the engine blocks are made with this, because you need a very high castability there. Because if you carefully observe an engine block, you have a it's a very intricate casting, because you want to have high cooling rate possible, so that you provide lot of fins on the surface. And if you want to have such fins in a mold, if you create a mold with such fins, that means you have very intricate holes into which the liquid metal has to flow. So that means the liquid should have very high fluidity. If it does not have fluidity, it does not flow into those regions, and as a result you cannot get such a fine casting. So that is one of the reason. The second most important reason is aluminum silicon alloys have, yes, coefficient of thermal expansion is almost 0. That is another reason why we use them. So if you look at that aluminum 7 silicon alloy, you have, because it is a hypoeutectic alloy, it has two micro constituents. One is a proeutectic phase, which is the proeutectic phase here in aluminum 7 silicon alloy. Alpha aluminum, it is a hypoeutectic. In an aluminum silicon, hypoeutectic consists of alpha aluminum grains and eutectic mixture. And what is this eutectic mixture? It is nothing but aluminum plus silicon, and this silicon is usually in the form of needles, and that is why this alloy is usually very brittle. So as a result, if we can somehow do two things, one is to make the grains finer, alpha aluminum grains finer, and second, if you can make the silicon needles into spherical particles, which is called modification. So if one can do these two, one is the grain refinement, second is the modification. If we can do these two things, we can have an alloy which is not only strong, but at the same time quite ductile. And that is what if we can try to see. For example, this tells you about grain refinement. If you take aluminum 7 silicon alloy, if you try to cast the alloy without any grain refinement, this is the type of macro structure that you get. It will not be columnar grains, as you have seen in the case of pure aluminum. The moment you have an alloying element, you will not always get the columnar grains. This is what is called constitutional supercooling. You must have read about it. So because of that, you will always get what are called coarse equiaxed grains whenever you have alloys. In case of alloys, you rarely end up in columnar grains, unless the alloy casting is too big. If it is a very big casting, then you will have some columnar grains, and at the center again coarse equiaxed grains. So this is the typical structure, macro structure, and this is the microstructure that you get. And if you do grain refinement, you can see the fineness of grain sizes that you can achieve, and also if you look at this the microstructure, you see finer grains. But what is important is look at the grain boundaries. At the grain boundaries you have this eutectic mixture, and this eutectic mixture, if you look at the high magnification, those silicon needles which you have at the grain boundaries, they do not get refined by the addition of the grain refiner, because grain refiner basically consists of particles which are TAL3, TAB2, this kind of particles, which can only act as nucleating sites for aluminum. They cannot modify the silicon needles. What is the mechanism of modification of silicon needles? We add sodium and strontium kind of elements, which are basically surface active agents, and these surface active agents form as a coating on the silicon particle once it nucleates, and prevents it to grow in a direction which is most favorite direction for the growth of these materials, because these are diamond cubic structures. Silicon is diamond cubic, so it tends to grow in a particular direction, giving it a needle like structure. So if you add this kind of surface active agents like sodium, strontium, antimony, this kind of elements, these elements have, you do not need to add very large quantities, very small amount, 0.01 to 0.02% is the one amount that we usually add. So if you add just about 0.01 to 0.02% of either sodium or strontium, these elements will go into the liquid, dissolve into the liquid, and when the silicon starts nucleating during the eutectic solidification, at that point they will coat that silicon and then prevent it to grow as needles, and that is what you try to see here. If you look at an aluminum silicon alloy and do not add any modifier, you see this is the type of silicon needles that you can get. This is a high magnification picture to show you what are the needle type of structure of silicon needles, and the moment you add 0.02% of strontium, the same silicon has become very fine particles. This is what we call modification, and unfortunately if you hold it for a very long period, 120 minutes shown here, this one is after 5 minutes of adding the strontium. On the right side what you have is after 120 minutes of holding that strontium. When you add the strontium into the liquid metal, hold it for a very long period, you lose whatever modification you have gained at a short holding time. This is what is called fading. Okay, why does it happen? It happens because strontium has a tendency to form some complex compounds with aluminum. For example, Air4Sr is a compound which forms with aluminum. So the moment you keep strontium which is inside the liquid for a long period, this strontium will react with the both the aluminum, and also people have also found out recently some other complex compounds with both aluminum and silicon. Okay, this it's a complex compound of aluminum, silicon, strontium, kind of a ternary compound. So once these compounds form, the strontium is lost from the liquid metal. So all the strontium comes out of the liquid metal and forms these particles, and so there is not sufficient strontium left out in the liquid to form as a coating on the silicon during its growth, and as a result you lose the strontium. In fact, sometimes we have also done adding excess amount of strontium can overcome this kind of problem. So people sometimes add more amount of strontium so that at least some strontium is left out to act as a nucleating site. So whenever somebody wants to use it for a long period of holding, he has to probably add higher amounts, but at the same time one does not want to add too much of an amount, because these particles which are forming, for example Al4Sr, are complex ternary compounds, will act as probably as brittle compounds present in the matrix and act as what are called stress concentrations inside the matrix, so that the strength of the and the ductility of the alloy might come down. So nobody wants to add too much of strontium or any compound forming elements into an alloy. So one has to remember that. So if you do combined addition, what do you do? For example, if you don't add any grain refiner or any modifier, this is what you get. You get dendrites of aluminum and needles of silicon. So this small picture which you see here is an enlargement of this eutectic mixture. So you see the dendrites of, the silicon needles in the magnified image here. And similarly, if you do grain refinement come modification, you can see the grain size becomes very fine. From here to here you can see the grain refinement has taken place, and in addition look at that any of those small region at the grain boundary, magnify it, this is what you see, that the grain boundary magnified image shows you a complete modification of the silicon needles. So one can have a combined effect of these two, and once you do that, the mechanical properties of such alloys are going to be much higher, and that is what you see here in terms of wear resistance. People have also done the yield strength of these alloys, and then you can see that usually the yield strength follows a Hall pitch type of a relation. Here is an example which shows you the wear resistance of an alloy also follows a Hall pitch type of a relation. How do we do this? You do a wear test on an alloy with different grain sizes, and once you know how much wear has taken place, how do we measure wear? How does a person quantitatively measure wear? Loss, amount of the weight loss or height loss, depending on the type of machine that is available to you. Nowadays there are a number of machines which are available, they can give you online height loss. So once you measure the height loss, you convert it into volume loss once you know the cross section, and from the volume loss one can also convert it into weight loss, or volume loss itself can be represented as the extent of wear. And this extent of wear, once you know, calculate the wear rate as a function of time, and once you know the wear rate, take the reciprocal of that wear rate, that is what will tell you what is called wear resistance. Reciprocal of wear rate is nothing but the wear resistance, and here we are trying to plot the wear resistance as a function of grain size to the power minus half, and you see exactly it gives you a Hall-Petch type of a relation. So, to show you not only the yield strength of the material, but also wear resistance of a material follows a Hall-Petch relation, and the fit is very good, 0.98. So, to tell you that all points, these are all from a very small grain size means here, the d to the power minus half is very large, means very small grain size. So, very large grain size is here. So, in a wide range of grain sizes one can show this, but the moment you go from a pure metal aluminum to an aluminum silicon alloy, you do not see such kind of a Hall-Petch relation here. The reason here is it is not a single phase material anymore. Aluminum silicon alloy has silicon particles along with aluminum grains. So, as a result, if you plot the d to the power minus half, here if you carefully observe, it is not the grain size which is plotted. What is DAS? Dendritic arm spacing. In case of alloys, we do not measure the grain sizes, because we always get dendritic type of growth in case of alloys. So, and because of which we always measure interdendritic spacing, and once you get an average interdendritic spacing, you plot the interdendritic spacing to the power minus half to the wear resistance, and when you do that, you will see this kind of a relation, parabolic kind of relation. This comes basically because of the silicon particles which are present in. So, you have a combination of the grain boundary strengthening and particle strengthening, that means precipitate kind of strengthening. So, a combination of these two will give you this kind of a thing. When you have very fine grain sizes, when you have grain size being very fine, the particles are also very fine, because when you have large number of grains, you can see the grain boundary area is very small. So, because the grain boundary areas, that means the grain boundary thickness becoming very small, you will see that in that region the silicon particles will become very fine. So, as a result, there is a possibility of silicon particles being very fine here in this domain, and as a result you get much higher strength, which is a combination of grain boundary strengthening and a precipitate kind of strengthening or dispersion strengthening. So, this is what you see, and one can also improve what is called the load bearing capacity during wear properties, particularly aluminum 7 silicon alloys, because they are used for wear resistance applications. What is the effect of such kind of a grain refinement on the load bearing capacity, if you look at it? So, if you try to take an aluminum silicon alloy which is not grain refined and try to conduct wear test at different loads, 50 newtons, 60 newtons and 70 newtons, you see the moment you use a low load, this is the type of wear volume loss as a function of time you will get. This is done at a one particular speed of the disc. Do you know how people measure the wear properties? There is a particular machine people use it. What is that called? Pin on disc, correct. It is called pin on disc machine, where you have a disc which is rotating at a high speed. You can control the speed of that disc, and you make your sample in the form of a pin and allow it to come in contact with the disc, and you measure as a function of time how the height of this pin, which is made in the form of a particular ASTM standard diameter and a particular height, and this material is allowed to freely stand on the disc and keep on increasing the load. You can have various loads on this particular pin, so that we can study what is the effect of load on the wear volume. And that is what, if you do it, as you increase the load from 50 to 60, the wear volume increases, and if you go to 70, then immediately the material seizes. That means the wear volume becomes so high that the material seizes. So, that means the pin gets stuck to the disc and it does not move anymore, and that is what you see if you do not do grain refinement. If you do grain refinement, you see there is no such seizing, but what you see is that with increasing load, definitely the wear volume is again increasing, but you can see after grain refinement one is able to increase the load bearing capacity of this. And if you go further, this is for 2 meters per second, same conditions. Here you can see 50 newtons alloy gives you a wear volume like this, and if you use 60 newtons, again you have seizure. At a higher speed, seizure occurs at a lower load. This is understandable very easily, because you are doing at a very high speeds, so as a result the tendency for the material to seize is much higher, the wear volume is also much higher. So the same thing if you do after grain refinement, you can see 50 and 60 give you some wear volume, but 70 seizes here. So that means even after grain refinement at certain load the material seizes. So one can do all this, and here we show you the effect of all 4 conditions. One is without grain refinement and modification. If you don't do any grain refinement, any modification, this alloy at a particular speed, if you do it, you see after 70 newtons it seizes. The wear resistance becomes 0 after 70 newtons. Now you do grain refinement, what happens? At 70 newtons the material has certain wear resistance, it is not 0, but as you increase further, once you reach 120 newtons the material again seizes. That means the wear resistance reaches a 0 value there. Now you do modification, only modification, you can see the material again at 120 newtons it has some wear resistance. So actually you can see from this very clearly that the modification has a better improvement in the wear resistance than grain refinement. Grain refinement basically only decreasing the grain size, whereas modification is changing the silicon particle morphology, and silicon particles are the one which basically give you high wear resistance because they are hard particles. It is like you take a ductile material, put hard particles into it, you can improve the wear resistance of a material. So similarly here you have hard silicon particles inside the material, you can have higher strength, a higher wear resistance. But you can see if you do combination of these two, grain refinement plus modification, here the only modified alloy seizes by 200 newtons. Here a combination of these two, even at 200 newtons it has not seized. It still has certain amount of, though you can see clearly the wear resistance is decreasing with increasing load, but still it has some finite value of the wear resistance. So this clearly tells us that a combination of grain refinement plus modification will not only increase the yield strength of the material and also increase the toughness of the material, but also improves the wear resistance of the material and the load bearing capacity during wear. This is practically very important whenever somebody wants to use such materials. That is why the grain refinement has become very important. Recently the DRDO labs are showing a lot of interest in improving the wear resistance of the materials of aluminum silicon alloys by a combination, proper combination of grain refinement and modification. Okay. So this is as far as the pure metals, and we looked at just one part, which is the aluminum silicon. Let us look at alloys in general. When you look at alloys in general, what are the strengthening mechanisms? There are number of them. We start with the same things which we have already talked. The first 4 are the ones we have already talked. They exist even in pure metals also, that the dislocation strengthening, grain boundary strengthening, vacancies and stacking faults. Only thing is the stacking faults strengthening gets either enhanced or decreased depending on the alloying elements that you add. So in case of alloys, the stacking fault strengthening depends on the type of alloying element that you are adding. Some alloying elements will increase the strengthening, some alloying elements will decrease the strengthening depending on whether they are increasing the stacking fault energy or decreasing the stacking fault energy. That is going to decide the strengthening which is coming because of the stacking faults. Whereas the dislocation strengthening, again another point also one has to remember, the alloying elements that you are adding can also act as pinning agents for the dislocation. For example, I do not know whether you have read, probably you must have read in detail about yield point phenomena. Yield point phenomena is just because of carbon atoms, isn't it? It is the carbon atoms which give you the yield point phenomena. Even strain aging we talk about. Strain aging is also related to carbon atoms, what is called drag, quartal atmospheres. You have read about all this. So, quadrilateral atmospheres are nothing but the dislocation which has the strain field, the stress, the tensile and the compressive components of the strain field above and below the dislocation. And once you have such kind of a situation, the moment a carbon atom goes there or any other solute atom goes there into those vacancies which are existing either below the positive edge dislocation or above the negative edge dislocation. Once the solute atom goes there, then it nullifies that particular strain field, and because of which it can lock up the dislocation moment. So, that is why we talk about the strain aging quadrilateral atmosphere causing. So, alloying elements can be a strong what are called the strengtheners. One of the most important strengthening that comes from alloying elements is what is called solid solution strengthening, and usually this solid solution strengthening looks something like this. If you look at a strength, yield strength as a function of percentage B, let us say, you will see this kind of a plot. If this is the yield strength of pure A, this is the yield strength of pure B, the strength reaches somewhere in the middle. It may not be exactly 50-50, it depends on the type of A and type of B, but somewhere it reaches maximum. And that is basically because when B goes into A, element B always has a different atomic size than that of element A. So, once the atomic size is different, then there is a misfit strain, and once this misfit strain is there, that gives you strengthening, and that strengthening we talk in terms of here. We can also talk in terms of when we talk about particle sizes, we will keep it for the time being, and then when we come to the precipitates, we will talk more about it. So, this is in general the strengthening that comes from because of the solid solution, which is basically related to the misfit, which is called delta parameter. What is delta parameter? Delta parameter is nothing but RA minus RB divided by RA mod of it multiplied by 100 in terms of percentage, where A is the solvent and B is the solute, and you normalize it with respect to the solvent all the time. So, that is what is called misfit parameter. The higher the misfit parameter, the higher will be the strengthening. So, whenever you take a particular solute atom and solvent atom, so, and keep on adding different types of solutes, the extent of strengthening is going to be different for different elements, because the misfit parameter is different for different elements. So, for example, iron, if you take the strengthening that you achieve because of various solute atoms is going to be different for different elements. So, same thing which we will see when we talk about superalloys also, the different alloying elements will give you different solid solution strengthening. So, which basically depends on this, and not only solid what are called substitutional solid solutions, interstitial solid solutions also give you strengthening in the same way. That there also what is crucial is the misfit parameter once again. So, this is as far as the solid solution strengthening is concerned. Once you come to precipitate strengthening, there are two types of precipitates, ordered precipitates and disordered precipitates. And if you have ordered precipitates, you have the strengthening that one can achieve is going to be much higher than what you can achieve with the disordered precipitates. Why? Because when a dislocation has to move through a ordered precipitate, it has to break the precipitate, cut through the precipitate, particularly if the precipitate is very fine. You must have heard about precipitation strengthening at some point of time, where we have two types of strengthening coming whenever you have precipitates. One, when a precipitate is very fine, what we call precipitate shearing takes place when the particles are very fine. When the particles are very big, we have what is called bowing taking place, over-on bowing which takes place. And when the precipitates are very fine in the range of what are called GP zones, you have the strengthening coming because of the strain field around those zones. There are not really any precipitates there, we cannot really see precipitates because they are so fine of just a few nanometers, maybe 1 or 2 nanometers. So, such zones can give you strengthening because of what is called the strain field around that, and that is what is given here. Whenever you have coherent strain field because of the particles and that gives you strengthening which is proportional to the misfit, which is epsilon here, and F, which is the fraction of such zones, which is nothing but volume fraction of precipitates we say. So, here they are not really precipitates, one cannot really see precipitates if you go to a microscope, one can only see strain contrast in a even in a electron microscope to distinguish between those so called precipitates, if you want to call them. That is why people do not call them as precipitates, they would prefer to call them as zones, GP zones we call, Guinier-Preston zones. So, the volume fraction of such zones and the what is called the misfit parameter there. Here the misfit parameter basically means the lattice parameter mismatch. If you have a precipitate that is forming, what is the lattice parameter of the precipitate and the lattice parameter of the parent phase, and this misfit is what gives you the strengthening there. And if one does more detailed modeling, he gets equations like this, which is given here. This is a rough estimate, and here you can see not only the volume fraction of the precipitates, but the misfit parameter, but also the size of the precipitate zones come into picture, and the Burgers vector also comes into picture, and the shear modulus of the matrix comes into picture. So, this is what is the strengthening that one can achieve because of the strain field. And once the particles become slightly bigger, but still finer, and that you have still some kind of semi coherent or coherent precipitates present, there you have two possibilities. One is shearing. Whenever you have particle shearing take place, this is what is the type of strengthening that you can achieve. The delta sigma is given by 2 under root 6 by pi, which is a geometric factor, because we are assuming either spherical particles or any type of elongated particles. By changing the shape of the particles, one can change this geometric factor, and what is important here is gamma, which is called the surface energy or the interfacial energy. Why this is important? It is important because when you take a particle and if a dislocation which is moving on a plane shears this particle, what kind of a situation you have? You have a situation like this. The particle gets sheared. When a particle gets sheared, then you are creating a new surface, and this new surface is given here. This is the new surface that you are creating. If I enlarge this, and this portion is the new surface that you have created. So, once you have created a new surface, for creating any new surface you need some energy to be spent. That is why we say nucleation during solidification also, we always say there is certain undercooling required for nucleation because surface has to be created. So, similarly, because the surface has to be created there, one has to provide extra stress to create that surface, and that is why the strengthening will increase, and that is why here it is very important to talk in terms of the surface energy. Surface energy is very is directly the strengthening that you can achieve is directly proportional to the surface energy. The higher the surface energy per a unit area, the amount of energy that you have to spend is going to be higher. So, the amount of stress that you have to give in is going to be higher. Similarly, it is also a function of the volume fraction, directly proportional to the volume fraction and indirectly proportional to the size. Why indirectly proportional to the size? Because surface area to volume ratio is going to be higher the finer the size, and we are talking of new surface being created. So, as a result, the total amount of surface to be created is going to be higher the finer the particles. So, that is why the finer particles will have higher strengthening coming into picture, and this is for shearing. And once the particles become much bigger, you have what is called dislocation bending taking place around the particles, because now the particles are much bigger. So, shearing is very difficult. So, dislocations cannot shear. So, instead they would like to bend around the particles, and that when they try to bend around the particles, we call it as Orowan bowing. Orewan is the person who has talked about this, and this particular Orewan bowing can be represented in this form, where delta sigma is what? Is sigma yield stress minus sigma naught basically. Okay. So, that is the increment in the strengthening that is taking place because of such precipitation. If you do not have precipitate, you have certain strength. If you have precipitate, what is the extra strengthening that you get? So, that is why in all these cases whatever we are talking about is the delta sigma, the extent of strengthening, additional strengthening that we are going to get, and that is proportional to the G Burgess vector and inversely proportional to the lambda. What is the lambda here? Interparticle spacing. Whenever you have precipitate strengthening, one of the most crucial aspect, in fact I would say there are three aspects which are very important whenever we are talking of precipitate strengthening. One is the volume fraction of the precipitates, two the size of the precipitates, three the interparticle spacing, and of course the fourth one, which is also crucial, is the surface energy, which we have talked about it just now. So, these are the four important parameters which decide the extent of strengthening that one can get. So, here the lambda is very crucial. So, as you can clearly see, lambda comes in the denominator. Obviously, it has to come in the denominator, because if the lambda is smaller, that means interparticle spacing is smaller, that means number of particles in a unit volume is higher, isn't it? So, interparticle spacing being smaller means the number of particles in a unit volume is higher, or in a particular direction. Even if you think of in a particular unit direction, unit length also is going to be higher if the lambda is smaller, isn't it? So, lambda is wavelength and wave number is inversely proportional to the wavelength. So, the wavelength number is going to be larger if the lambda is smaller. So, as a result the number of obstacles are going to be higher if the lambda is smaller. So, that is why lambda comes in the denominator, and again the particle size also comes into picture. And one can also talk in terms of a Hall-Page type of a relation in case of precipitates in terms of lambda to the power minus half. So, one can plot the yield strength of a material as a function of lambda to the power minus half and get again a linear relation. So, this is as far as precipitate strengthening is concerned. And one can also talk about ordered precipitates, which we have not talked so far, and in case of ordered precipitates you get an additional parameter here which is called gamma APB. What is this APB? Antiphase boundary energy. Okay. So, whenever an ordered particle is there, if an ordered particle is sheared by a dislocation, so you are creating an antiphase boundary. So, if an antiphase boundary has to be created, again as I told you before, like a particle shearing, one has to create certain new surface, so one has to spend energy. The extent of energy that you have to spend is going to depend on how much is the antiphase boundary energy. If the antiphase boundary energy is higher, you have to spend more energy, that means more stress. So, that is why you can see this comes in the numerator, it does not come in the denominator. This is very crucial for you to understand. So, in any strengthening, what comes in the denominator, what comes in the numerator is very important. Okay. So, this is, and again R comes into picture, the size of the precipitate particle, the volume fraction of the particles. Okay. So, this is what is called precipitate strengthening. Then let us talk in terms of the other aspects. Once precipitate strengthening has occurred, we know that precipitate strengthening, yes, it depends on here in case of these particles. If the particles are bigger, okay, here in this particular case, if the particles are bigger, what would be bigger, you tell me? That is what I am saying. You can see del sigma is increasing with R. Only thing is it is not directly proportional, it is to the power half. So, you can clearly see that the strengthening that you can achieve because of R is much smaller than the strengthening that you can achieve because of gamma. So, that is why gamma is much more crucial here. So, antiphase boundary energy, because it is 3 by 2. So, one has to consider that. So, once you have these particles, And once we go to higher temperature, we come into a problem of particle coarsening, isn't it? Once particles coarsen, what is going to happen? The number of particles are going to decrease, because the total volume fraction of the particles has to remain the same, isn't it? The total volume fraction of the particles has to, in fact, you will see this is one important point that one has to remember. Does the volume fraction will remain the same once you increase the temperature? In principle, it will decrease. Why does it decrease? Think of your phase diagram, temperature versus concentration. Look at this, the solvus line. You consider a particular alloy, and the extent of supersaturation at room temperature is this, and the extent of supersaturation at high temperature is this, for the same alloy. So, if the supersaturation is decreasing, volume fraction is decreasing. In addition, for a given volume fraction, if the particle size is increasing, it means that some particles are becoming bigger at the expense of obviously some other particles. We have talked about this during thermodynamics class, that some particles dissolve and some particles grow, and as a result the number of particles decrease when the particle size increases for a given volume fraction. So, if the number of particles decrease, then the interparticle spacing is going to increase, isn't it? So, if the interparticle spacing increases, then the strengthening is going to come down. So, two things are going to happen when we go to high temperature. One is the volume fraction is decreasing because particles are dissolving. Second, the particles are becoming bigger, because of which the delta is decreasing, and if the delta decreases, then you can see the strengthening decreases. As a result, our goal is to how to control the particle coarsening, and that is where lot of people have done a lot of studies, and people have come up with an expression of this kind, where dr by dt tells you what? Rate of increase in the particle size. That means grain particle coarsening. I should not call it grain coarsening here. The particle coarsening. So, you have a number of particles, and these particles are trying to coarsen. So, the rate of coarsening of the particles is dr by dt, and that is proportional to d. What is d? Diffusivity. Obviously, it is very easy to understand why it should be proportional to the diffusivity. If the higher the diffusivity, the faster is the diffusion. So, easy particle coarsening, because particle coarsening occurs only because of diffusion. Otherwise, if there is no diffusion, there is no particle coarsening. Then the second thing is gamma. The higher the surface energy, the easy for the growth coarsening. In fact, that is the reason why if somebody wants particle coarsening not to occur, you need to create particles which have very low interfacial energies, ordered. Coherent particles do not grow as fast as non-coherent particles. Incoherent particles grow very fast, and semi-coherent and coherent particles do not grow because they have lower interfacial energy. That is why that is very important. Second thing is the solubility. Xe is the equilibrium solubility. If the equilibrium solubility is very large, then particles will coarsen very easily. If the solubility is very small, then they do not coarsen, because for coarsening of some particles have to dissolve, isn't it? So, as a result, solubility is going to decide the coarsening indirectly. So, that is why if you have two different phase diagrams, one phase diagram like this, another phase diagram which is like this, where the solvus line is much more steeper, this kind of phase diagram, in this alloys the coarsening will not occur very easily. In this alloys, coarsening will occur very easily. So, solubility is very crucial, and it is also inversely proportional to the average particle size, square of the average particle size. That means, if the average particle size is very large, then the coarsening is lower. If the average particle size is very fine, then the coarsening is higher, because fine particles have a greater tendency to coarse, isn't it? Okay. So, because of high surface area to volume ratio, So that is why this is going to be very important. So all these factors have to be considered, and that is why when somebody thinks of alloy design, people consider all these. For example, why do we use dispersion strengthening? Because of this. For example, one important thing for dispersion strengthening is this: Xe is almost 0. But definitely gamma is going to be higher, so one has to consider that aspect also. Okay, so how are we going to have an advantage or a disadvantage? One has to look at the actual numbers and then decide whether we are going to have higher strengthening. Definitely. So whatever may be the gamma, if Xe is 0, then dr by dt is 0, isn't it? So that also one has to consider. Okay. So other way is also that grain boundary coarsening also is very important, because we know the strengthening comes because of grain boundaries. So if at higher temperatures grains also tend to grow, so we have to think of how to prevent grain growth. So for that, one way is to do what is called grain boundary pinning, and this grain boundary pinning depends on the particles. So if you put hard particles which can go to the grain boundaries and can pin the grain boundaries, and the volume fraction of the particles and the size of the particles are going to decide what is the critical diameter of the grain size that you can achieve. If you have large volume fraction, then you have a smaller grain size. If you have very small, if for example if the volume fraction goes to 0, you can see d is almost goes to infinity. That means grain growth can occur very easily if you do not have any particles. So if you have a large volume fraction of particles, then the grain growth is completely controlled, so that the d is very small. So that is why one can also control the grain growth by controlling in terms of the grain boundary pinning agents. That is what we see in case of high strength low alloy steels or microalloyed steels. In microalloyed steels, we add certain alloying elements such as niobium, vanadium, titanium, which form carbides and nitrides, go to the grain boundaries and prevent the grain growth. So this is what is precipitates and dispersoids. And the other possibility is the second phase mixtures, the eutectics and eutectoid mixtures. Whenever you have a second phase, we get strengthening. And finally the martensite. We all know that martensite also gives strengthening. So these are all the various strengthening mechanisms. We stop here and consider the superalloys in the next class. Thank you very much.